Section 7.8, Convolution. To motivate what we're going to do in this section, let's take a look at a familiar example that we've looked at a couple of times in the past. Let's consider the inverse Laplace transform of the function 1 over s times s squared plus 1. Now we've seen this type of rational function and we've computed its inverse Laplace transform using partial fractions. But if you were to humor me for a moment, if you just look at the pieces of this fraction, 1 over s, we could write this as 1 over s times 1 over s squared plus 1. And if we were to write this rational function in this multiplicative form, this is not a partial fraction decomposition, just write it in this multiplicative form, we notice pretty quickly that this is a function that we individually know how to inverse Laplace transform. It inverse Laplace transforms back to 1. And this function we know how to individually inverse Laplace transform. It transforms back to sine t. And so the question then is, if I know how to inverse Laplace transform the pieces of this product, can I not just inverse Laplace transform this piece, inverse Laplace transform this piece, and then multiply them after we've performed the transform on the pieces? And the answer is no, you cannot do that. Matter of fact, to check that that's true, we would just do a partial fraction decomposition on this. We would find the actual inverse Laplace transform, and we would see that it's not this function. Of course, we can also see that the inverse Laplace transform of this function is not this, because if that were true, then the forward Laplace transform of sine t would be this function, and we know that this is not its forward Laplace transform. And the moral of the story here is that the inverse Laplace transform cannot be broken up over multiplication like this. We've seen the inverse transform distribute, in a sense, over addition and subtraction from linearity, but it's not multiplicative. You can't distribute this action over this multiplication. So the goal of this section is to invent or conjure up a type of function multiplication where this is true. And that might sound a little bit bizarre, but it's actually quite a common theme in mathematics when you have a structure that's tantalizingly close to something that would be very useful to you, and maybe you have an algebraic or arithmetic roadblock, then you look for ways to tweak that structure so that you can get the type of result that you're after. Of course, you have to make sure that it's logically valid, and so to complete that validation, we need to determine a new type or modified type of function evaluation. And that type of function multiplication is called the convolution or the convolution product of two functions, and we'll define the convolution as follows. The convolution of a function little f of t and little g of t is defined by f convolved with g. It will be a function of t, and we usually use a star or an asterisk, certainly something other than a regular dot that we would use for multiplication in the past, or conventional function multiplication. So we'll say f convolved with g, or the convolution of f with g, is defined to be the integral from 0 to t of f of t minus s times g of s ds. So this is a little bit similar to what we saw with maybe the integral definition of the Laplace transform, but it's very different in some ways. This is not an integral from 0 to infinity. We don't see an e to the minus st, but instead we should think of this new type of multiplication takes the function f of t and g of t. It converts a g of t to a g of s. It converts an f of t to an f of t minus s. It multiplies those two things and then integrates with respect to s. S here is the variable of integration, and you integrate with respect to s from 0 to t. So you can see that when the s's are integrated out, this will be a function of t. Now I fully admit at this juncture we have no feeling for this type of convolution multiplication. We can't presuppose any of its nice algebraic properties. We're really sort of going in with no bearings on what is happening here. So let's just get those bearings by looking at some examples. So let's compute the convolution product of the function t times t squared. Now we know that with regular function multiplication, this would obviously give us t cubed, but this is a new form of multiplication for us and we really don't have a feel for it, so let's just follow the definition. So here t is playing the role of our f of t squared is playing the role of our g of t. So looking at our definition, we need to go ahead and pre-compute f of t minus s, which would be t minus s. We need to compute g of s. If this is g of t, then g of s would be s squared. We need to multiply our f of t minus s times our g of s, and then we need to integrate that product with respect to s from 0 to t. So this is the integral formulation of the convolution product. Now when we do this, we're just going to treat t like a constant. We're going to integrate with respect to s. So why don't we distribute this s squared and then anti-differentiate with respect to s, keeping t fixed. When we do that, since t is fixed, we can split this integral up. We can pull the t outside of the integration because this is an integration with respect to s. And then we get two familiar integrals that we can use the power rule on. We anti-differentiate and evaluate between limits. When we do, we get this and we simplify and we get that the convolution product of the function t and t squared is 1 over 12 times t to the fourth. Now, like I said, we don't really know what that means or how we can make use of it. We're just getting to know this definition. But we also need to establish what are the algebraic properties of this new form of multiplication, how much do those familiar properties of multiplication carry over. And so let's look at the properties of the convolution product. First of all, f convolved with g is the same as g convolved with f. So this multiplication is commutative. The order doesn't matter in how you perform the multiplication. You can do first times second or second times first. It also plays nicely over addition. So f convolved with g plus h is the same as f convolved with g plus f convolved with h. So it's distributive. The convolution product distributes over multiplication. It's also associative. F convolved with g convolved with h is the same as f convolved with g, and then that convolved with h. So how you associate or write the parentheses here to group things doesn't matter across this multiplication. And last here is if you convolve f with a zero function, you will get the zero function. So this convolution product enjoys the familiar product called the zero property that we're used to with scalar multiplication. So a big question now is, why should we care about or invest in this newfound form of multiplication? If there's no payoff, then it really doesn't make sense to do so. But here is the payoff. It's the so-called convolution theorem. And the convolution theorem says that if you take the Laplace transform of f convolved with g, then you can just forward transform the little f to get big F, forward transform individually the little g to get big G, and then just multiply them. Remember in our example above, when we were doing inverse transforms, we said you can't break this action up and just take the inverse transform of the pieces. But what this theorem is saying is you can break the action of the Laplace transform up as long as you have the right types of multiplication going on. It's regular multiplication in the S domain. It's convolution multiplication in the T domain. That's very, very important point here. Now remember, anytime you have a forward Laplace transform theorem or formula, it's a 2-for-1 special because you automatically get an inverse transform. And so both of these come packaged as what's called the convolution theorem. So you can think of there's like a forward and a backwards, or a forward transform and an inverse transform version. And so the convolution theorem says if you take the Laplace transform of f convolved with g, you'll get big F regular multiplied times big G of s. But if you were to read this backwards, if you inverse transform this, then you will get this. So that's what this says. If you inverse transform big F of s regular times big G of s, then you can inverse transform the pieces. Think back to our first example in the section. You can inverse transform the pieces. You can't tie them together in the T domain with regular multiplication, but you can tie them together in the T domain with the convolution version of multiplication. So this makes convolution very much worth it because it allows a type of multiplicative structure, a modified multiplicative structure, with forward Laplace transforms and inverse Laplace transforms. So let's revisit the example that we started with. If you want to take the inverse Laplace transform of 1 over s times s squared plus 1, well, first you can write it as a product, and here's the key. You need to be able to write it as a product, and the individual pieces need to be things that you know how to individually transform. And that's very much the case here, because if we think of this as big F of s, then it's big F of s is 1 over s, so little f of t is 1 when we inverse transform. And then when we individually write this as big G of s, when we individually inverse transform, we get sine t. And so now we know from our example, you can't just write this as 1 times sine t. That's not correct. But our convolution theorem says you can write it as 1 convolved with sine t. And now we can compute this using our integral definition. This is playing the role of our f. This is playing the role of our g. So if this is f of t, then we would write f of t minus s times g of s integrated with respect to s from 0 to t. But since f is just the function 1, then f of t minus s is the function 1. If g of t is the function sine t, then g of s is sine s. Now we have just a straightforward integral of sine s ds. We anti-differentiate, evaluate between limits, simplify, and we get that the inverse Laplace transform of this rational function is this convolution product, and this convolution product comes out to be this function. And if you wanted to check me on that, you could go, and we already know how to find the inverse Laplace transform of this. We would just do a partial fraction decomposition, which notice is fundamentally additive, not multiplicative. You would break this up into a partial fraction decomposition, compute the coefficients, invert the pieces, and you would get this. And so you can see that you're sort of going to pay your taxes one way or another in computing this inverse transform. You can think of it that in a partial fraction decomposition, you're paying more of your taxes in the algebra realm, where you're finding the coefficients and inverting the pieces. And in a convolution theorem setting, if you choose to do this via the convolution theorem, you're paying more of your taxes by computing this convolution product, which results in an integral. Okay, so here is the details of doing this convolution. Instead of using the convolution approach, you could have used a partial fraction decomposition approach. We know how to do this, and this is just showing you that the convolution theorem can offer us a different methodology than the partial fraction decomposition. But that is not the only benefit. It's not merely a computational difference or maybe even a benefit. We can also use this to solve a very wide class of initial value problems where the forcing function is not known. So let's suppose we wanted to solve the initial value problem, y double prime plus y equals f of t, with the initial conditions y of 0 is 1, y prime of 0 is 0. And we're going to solve this for an unspecified forcing function f of t. And you can imagine where this might be very useful in many applied contexts, because imagine like in electrical engineering, if we had a second, it turns out that if you were to write down the differential equation for, say, an RLC circuit, it turns out to be a second order linear non-homogeneous constant coefficient equation, and this is our input into that, our input voltage. And so when you do that, this allows you, as we've done in the past, if you specify an f of t and you give a particular concrete form for f of t, then you could use undetermined coefficients, you could use variation of parameters, you could even use our past Laplace transform methodologies, but those methods would be inherently dependent on knowing what f of t is. And imagine in an electrical engineering setting, you want to envision maybe many different types of input voltages, and you'd like to study how that one circuit responds across 10, 20, 30, 40, 50 different input voltages. Or in a mechanical engineering context, imagine this is a spring mass system, and this is a forcing function, and you could individually solve 50 different initial value problems for 50 different forcing functions, but wouldn't it be nice to solve things with a general f and just do all the computations once with a general f and then plug 50 different f's in to see the responses to those forcing functions? That is something that can be accomplished with the convolution theorem in conjunction with Laplace transforms. So here we go. We're going to solve this problem where we're thinking here of f as a fixed forcing function, but we don't know what it is. So we'll take the Laplace transform of both sides. We'll use our differentiation theorems. We'll apply the initial conditions. We will do our normal thing. Now notice here we don't know what little f of t is. So when we go to Laplace transform it, the most we can say is whatever little f of t is, this is big F of s. Okay, so that feels different than the past. We apply the initial conditions. We factor out the big Y of s. We throw this extra term to the other side. We're going, sooner or later, we're going to divide by this, so we do it now. And now we're going to split this fraction into an s over s squared plus 1 plus a big F of s over s squared plus 1, just to keep the part that has the big F of s separated from this part that we do know how to handle. And now when we get to this stage, we can just take the inverse Laplace transform of both sides. When we do, since this is addition, we can break up by linearity. We can apply the inverse Laplace transform to the pieces. We know that this inverse transforms back to little y of t. And then we can take the inverse Laplace transform of the pieces. This is familiar to us in our basic table, and it inverts back to cosine t. This is something that right now we're not sure how to handle because I don't know what the function big F of s is, but we could take our big F of s and write this as big F of s regular times 1 over s squared plus 1. Now this looks like a convolution theorem situation because we are needing to invert a product of two functions in the s domain. And so we know that the way the story ends via the convolution theorem is we just invert the pieces, and in the t domain we connect it with convolution multiplication. So let's see how that plays out in this specific example. So remember, big F of s is just the Laplace transform of little f of t. So when we apply the convolution theorem, when we individually invert this, we get a little f of t. When we individually invert this, we get a sine t. We have to connect them together with a convolution product. That's the convolution theorem in action. And now we can rewrite this as an integral. This is the integral from 0 to t of f of t minus s times sine s ds. And this is very general. Now, I don't know how satisfying this feels to you at this point, but notice what we found highlighted in yellow. We know that the solution to this initial value problem, whether it represents a mechanical system, electrical system, or something else totally, we know that we have a formula for what little y of t is going to be. So if you wanted to try 50 different forcing functions, at least you don't have to go through all of this 50 different times. You can just plug in 50 different functions here, and it's a matter of just multiplying it by sine s, integrating it, and adding cosine t. And that's a pretty low overhead calculation, certainly if you were going to do this with a computer or calculator or something like that. So this is very, very general, and this is something we've not been able to accomplish up until now, where we could solve one of these unspecified forcing function problems when it was in fact unspecified. We always had to know what f was in order to use our other methods. So for example, here if you had in mind, well, I want to see how the circuit or the mechanical system responds when the forcing function is the square root of t. Well, I would just replace, if f of t is the square root of t, then f of t minus s is the square root of t minus s, and this is the solution. This is something I can put into my computer or calculator. I could graph it. I could evaluate its derivatives. I could evaluate its values. I could do all sorts of things. Same thing if f of t was t squared. Notice how low overhead this is. I just replace this with t minus s quantity squared, and there you go. That quickly, almost instantaneously, because I don't have to redo all this Laplace transform work. I've got the solution. If it's e to the t, then I get this. So very, very quickly, I can have lots of different forcing functions, and I'm free to calculate and or experiment as I like. Now the next topic we want to apply this convolution theorem process to is the topic of so-called transfer functions and impulse response functions. So we're going to back out for a minute to a general differential equation, ay double prime plus by prime plus cy equals f of t, we're going to purposefully pick what are called rest initial conditions. Think of this as a spring mass system. When it's at total equilibrium here, there's no initial displacement and there's no initial velocity. The system is at rest, and so we're giving these zero initial conditions. Zero initial displacement, zero initial velocity. So here, think of a, b, and c are numbers that are known, and little f is a function that is known. If we take the Laplace transform of both sides, we've done this many, many times. We apply our derivative theorems, we apply our initial conditions, we get to this juncture, and in the past we've solved for big Y of s, but here I want to do something a little bit different. I don't want to solve for big Y of s. I actually want to solve for the ratio of big Y of s over big F of s. So when I get to this line, we're used to solving for big Y, but here I want to do something different. I want to divide both sides by big F and divide both sides by as squared plus bs plus c. And maybe it's time to go off to the side and have a little terminology talk. Remember that for this equation, the homogeneous version of this equation would have a 0 here. And then the characteristic equation for that would be AR squared plus BR plus C equals 0. So here in blue, this would be the characteristic equation associated with the homogeneous version of this differential equation. This is called the characteristic equation. If you look at what's on the left-hand side, this is called the characteristic polynomial. So one little quick check that you can make when you're doing this work is when you have rest initial conditions. This is very important. When you have rest initial conditions, this left-hand side, when you take the Laplace transform, the left-hand side, because all of these are going to zero out, is always going to come out to be your characteristic polynomial times big Y of S. That's what's always going to happen. Notice the characteristic polynomial here is just, we're writing it in terms of S instead of in terms of R. But this is the characteristic polynomial. And now if you isolate not for Y of S, but Y of S over big Y of S over big F of S, you're always going to get 1 over the characteristic polynomial. So we're going to define the ratio of big Y of S to big F of S. We're going to define this as a new function called big H of S. And we can tell you how this story always ends computationally. Big H of S is being defined as big Y over big F, but that's always just going to be 1 over the characteristic polynomial. This big H is called the transfer function of the system. And the transfer function of the system is defined to be the Laplace transform of the output of the system to the Laplace transform of the input of the system. And so this always comes out to be, in these types of problems, it always comes out to be 1 over the characteristic polynomial. So then we're going to define, if this is the transfer function of the system, we're going to take the inverse Laplace transform of both sides of this equation. So the inverse Laplace transform of big H is the inverse Laplace transform of 1 over the characteristic polynomial. And that is something we know how to compute. If you give me coefficients A, B, and C, we know how to compute this. That means we know how to get our hands on this. And we call this little h of t the impulse response function for the system. So that's a kind of a winding road to get to the point of, if you have this kind of initial value problem, if you have this kind of system, there's associated with it a function in the h domain. It's not the solution. There's just this function associated with this system in the s domain, and it's called the transfer function, and that function is always 1 over the characteristic polynomial. And if you take the inverse Laplace transform of the transfer function, you get little h of t. It's always going to be inverse Laplace transform of 1 over the characteristic polynomial, and that is called the impulse response function of the system. So why would we care? Notice this is not a solution to the original system. So what is this creature? Why is this important? Well, suppose we want to solve the very, very general initial value problem where we take ay double prime plus by prime plus cy equals f of t. Y of 0 equals y naught, y prime of 0 equals y1. I mean, in a certain sense, it doesn't get any more general than this if you're going to talk about second-order linear problems. This is non-homogeneous with constant coefficients. It has unspecified initial conditions. This is very, very general. And so we'll call this problem 1. And now we want to break this problem up into 2 associated problems. We want to look at ay double prime plus by prime plus cy equals 0. So notice we're forcing it to be homogeneous, but we're leaving the non-homogeneous initial conditions. Think non-homogeneous, non-zero. So we have homogeneous differential equation, non-homogeneous initial conditions. Call that equation 2. Then we're going to do the exact opposite for equation 3. We're going to leave the differential equation as non-homogeneous, but we're going to make the initial conditions homogeneous. See how we're offloading? There's 2 non-homogeneities here. There's the forcing function f, and there's the initial conditions y0 and y1. So in the first one, we're going to offload and make the non-homogeneous part of the make the differential equation homogeneous, so get rid of this non-homogeneity, but leave these alone. And in equation 3, we're going to do the opposite. Leave this non-homogeneity, but erase this, leave this non-homogeneity, but then erase the non-homogeneity that occurs in the initial conditions. Now, let's call the solution to problem 2. We need a way to talk about this. We don't want to call the solution to this problem is different than this problem is different than this problem. So why don't we think of the solution to our overall guiding problem, we'll call that y. So we need a solution, we need a way to talk about the solution to this, and the book uses y tilde, so why don't we call the solution to equation 2 y tilde? And then the theorem says, the following theorem says, that the solution to the overall problem 1 is just y tilde, the solution to problem 2, plus the impulse response function convolved with the forcing function. Or if you write it in its integral form, you get this. So this is why we cared about the impulse response function for the system. It encodes a way to solve all of these very general initial value problems in one fell swoop. Here's all you have to do. Solve this equation 2 problem for y tilde, which is very doable. Look at this. This is a homogeneous differential equation. So we're way back to early chapter 4 with non-homogeneous initial conditions. This is the easiest one of these three to do. Solve this easy problem y tilde, but now you do have to go find the impulse response function, but that's not so bad. The impulse response function is just the inverse Laplace transform of 1 over the characteristic polynomial. Go get your hands on that function. That will be a function in the t-domain. Convolve it with f in the t-domain. And if you want to put it in its integral form, which is normally the way that what you'll have to do in order to do anything with it in real life, you put it in its integral form and you get this. This is a very, very general solution to a very general initial value problem. And that's why the impulse response function is so useful. Let's take a look at a concrete example. So suppose you have y double prime plus y equals f of t. Y of 0 is 1, y prime of 0 is 0. So we want to find the general solution to this. We want to find the solutions to these initial value problems. For any f, I don't know what f you have in mind. So first we're going to form the associated homogeneous differential equation, but leaving the initial conditions non-homogeneous. So this would be our equation 2 above. This we know how to solve. Go get the general solution of this as c1 cosine t plus c2 sine t. Apply the initial conditions, and when the algebra and calculus dust settles, you get that the solution to the highlighted yellow problem is just cosine t. So we'll name that y tilde. In keeping with our formulation above, we solved the so-called tilde problem, and we got that y tilde is cosine t. Now secondly, what do we need to do? We need to go find the transfer function associated with equation 3. And equation 3 needs to be, remember, we don't find transfer functions of these because they don't have 0 initial conditions. This is why we needed equation 3. So it's non-homogeneous differential equation, but 0 initial conditions. We can find the transfer function of this. It's just 1 over the characteristic polynomial. So here, highlighted in green is our equation 3. And then we just find the transfer function. It's 1 over the characteristic polynomial, 1 over s squared plus 1. To find the impulse response function, we just inverse Laplace transform this guy. And when we do, we get sine t. So that's our little h of t. So now we put it all together. The overall solution to the given problem is y tilde plus h convolved with f as a function of t. Y tilde we found above was cosine t. We found that h was sine t. So we want to do h of t minus s, so that's sine of t minus s. And our f is a function that we haven't specified. So if you don't know what little f is, this is the best that you can do. And if you have 1, 2, 3, 4, 5, 6 different little f's in mind, then you can put 1, 2, 3, 4, 5, 6 different little f's in here, and you can get your different solutions. But this is very, very powerful. Notice how clean this was. Notice it wasn't nearly as messy as what we've done in the past. And the real reason for that is we've used some very high-powered machinery to do this. So even though we don't have all the tedium that we had in the previous methods, we're actually cutting through that tedium with the deep theory of the Laplace transforms and the convolution theorem.